Okay, I'm going to try one more time to see if I can get this video recorded because it wouldn't work the last time and my computer died, so that's why this video is in two parts. So, where we left off from the last video was we started plugging in negative x into the equation. If you're trying to figure out whether it's symmetric with respect to the y-axis, you plug negative in for x and you leave the y alone. So the y here, we're going to leave it alone. Oop, let me make this bigger, sorry. We're going to leave the y alone. We're going to change the x to negative x, and we're going to change this x to negative x also. But what happens when you change this to negative x? Negative x to the fourth power is basically like negative x times itself 4 times, which is going to turn to a positive. So that stays positive x to the fourth power. Negative x squared is negative x times negative x was just going to become x squared again. And so you basically have this equation. Now the question that you're going to ask yourself is this the same as the original equation? This guy right here is what we ended up with. This is what we started with. So yes, that's the same. So since they are the same, this is symmetric with respect to the y-axis. Okay, x-axis symmetry. If you think about our wonderful point 2,3, if you reflect them across the x-axis, what happens is the y-coordinate becomes negative. So that changes from 3 to negative 3. And xy is going to be replaced with x negative y. So the x is going to stay the same, but the y is going to become negative. So down here, if we're trying to check that, we replace this y with negative y. We leave this x alone, and when we take negative y and we square it, trying to get rid of the parentheses, negative y squared is going to just become y squared. 4x minus 12 stays the same, and then we look to see, is this the same thing as the original? Yes, it is. So it is symmetric with respect to the x-axis. Now this is the graph of a function like x equals y squared that is symmetric with respect to the x-axis. And if you notice this guy, he is technically not a function because if you do the vertical line test, straight up and down, he passes at more than 1 point. So he is technically not a function. Things that are symmetric with respect to the x-axis are not. So we'll talk more about him here in just a second, but the third type of symmetry, the third and last type of symmetry is symmetry with respect to the origin, and that looks like something over here, kind of like y equals x to the third power is origin symmetry. And origin symmetry is if you take a point that's up here, he's kind of like a reflection across the x-axis and then a reflection across the y-axis. Or you could do it this way and then that way. You can do y-axis and then x-axis. It doesn't matter in that case what order you do them in, but origin is like a combination between x and y reflections. So xy is replaced with negative x, negative y. So both of them in that case become negative. And we'll see that on the back side here. So this guy, I went ahead and wrote out the equation again, or the rule, I guess. Xy becomes negative x, negative y. So we're taking and we're plugging it into this equation. Y is going to become negative y. X is going to become negative x, and x becomes negative x. So negative y is just going to simplify to negative y. Negative x to the third power, if you take a negative times itself 3 times, it stays negative. And then minus a negative x becomes positive. So this right here in the blue is not the same thing as what we had to start with. But if I take and multiply everything by a negative 1, it does become what we had to start with. So that's something else that you need to look at, in particular when we're doing something, when we're doing origin symmetry. A lot of times, if you are able to multiply it by a negative 1 and get it to be the same, then that still counts. So it is still the same as the original if you multiply both sides by a negative 1. So yes, it is symmetric with respect to the origin, all right? So this rule right here, this box right here, is basically summarizing all three of those. So negative xy is the y-axis, x negative y is the x-axis, and origin is negative for both. So then they get down here and they start talking about even functions versus odd functions. It's an even function if it's symmetric with respect to the y-axis, like y equals x squared. He's a parabola with symmetric with respect to the y-axis. Now that is only if he's not shifted to the left or to the right. If he's over here on the right side, he's not symmetric with respect to the y-axis. So that's a little bit different. If it's just like y equals x squared, he's symmetric with respect to the y-axis. He's symmetric with respect to the origin makes him an odd function, like y equals x to the third power. He is this guy right here, and he has origin symmetry, all right? It's kind of goes with the fact that an even function is x squared, where 2 is an even number and 3 is an odd number. So that's what makes him, those kind of even and odd functions is how they're named. Now, it's good to point out that not every function is either even or odd. Sometimes you'll have neither occurring, and that's a case where we have like x minus 3 to the third power. This guy is shifting him to the right 3 units, so it's my same x cubed function to the right 3 units. And he now is not an odd function. He's not symmetric with respect to the origin anymore. So you can have functions that are neither even nor odd, and that would be like a scenario like this. So just because he's x to the third power doesn't necessarily make him an odd function. A lot of functions are neither even or odd. Okay, and then we talked a little bit about is there a function that you can have that is both even and odd at the same time, and the only time that will occur is if you have like something like a circle. So x squared plus y squared equals 9. This thing is a circle with a radius of 3, because the square root of 9 is 3, and he is, you can reflect him across the y-axis, and he has origin symmetry also. So that's the only time you'll have an even and odd function at the same time. Otherwise, if you have a function that is even, you don't need to even really test it for odd, because we already know that he's going to be not odd if he's even. So there you go.